All right, guys. So I wanted to go through the final with the answers on it, the final review, sorry, with the answers on it, so that if you want to hear it as you copy it down or having a hard time reading it, that you can actually hear it as you go through it and might help you out. Okay. So in Unit 1, Number 1, where it says match the scientist with what they study, we see here that hydrologist, okay, hydrologist, well, we have hydro here, meaning water. So hydrologist would study the movement and distribution of water and ice on Earth. So hydrologist, okay, right here, movement and distribution of water and ice on Earth. Okay. Now, what would a meteorologist study? Well, a meteorologist does not study meteors. They study the weather and the atmosphere, okay? So they'd be right down here, Earth's atmosphere and weather. Then you have an astronomer who would study meteors or space objects, and therefore they would study the planets. And then a geologist would study the rocks on Earth. Okay, so real quick, again, hydrologists study the movement and distribution of water and ice on Earth. Meteorologists study Earth's atmosphere and weather. An astronomer would study the planets, and a geologist would study the rocks on Earth. Moving on to the next one. We want to see if I can get this up here so it's out of the way. There you go. Matches the vocabulary and concept or example. So a hypothesis. What is a hypothesis? So look down through here. I see right here it says an educated guess based on previous data. So hypothesis is an educated guess based on previous data. Okay. A theory is something that has to be kind of proven over a long period of time, studied for a long time, and experimented for a long period of time. So we see it happens after a scientific experiment to test a hypothesis produces the same results over a long period of time. Okay. So that is B right there. Then a conclusion. Okay, conclusion is our interpretation of the data that we saw in the experiment. And then analyzing or analysis is using mathematics on that data. Okay, whoops. So analysis is using mathematics on the data. All right. So again, we got hypothesis. It's an educated guess based on previous data. Theory comes after scientific experiments to test a hypothesis produces the same results over a long period of time. Conclusion is the interpretation of data, and analysis is using mathematics on that data. Number 3, looking at different types of conservation. So the conservation of energy, okay, states that energy is neither created nor destroyed. It just changes or is transferred. So energy or conservation of energy states that energy is neither created nor destroyed, just changed or transferred. The conservation of matter is very similar, that matter is neither created nor destroyed. Okay, it can only be moved or changed. So if I'm crushing a rock and it produces heat, okay, and this flows into the atmosphere, this would be an example of the conservation of energy because we're talking about heat. See that? Heat and energy, so the conservation of energy. Then down here, a large rock is weathered into tiny pieces, which add up to the weight of the original rock is an example of the conservation of matter. Conservation of matter. Number 4, energy. Define kinetic energy. It is the energy of motion. Kinetic energy is the energy of motion. Define potential energy, that is energy stored in an object. Define potential energy, the energy stored in an object. A roller coaster going up a hill is an example of kinetic energy being converted to potential energy. So a roller coaster going up a hill is an example of kinetic energy being converted to potential energy. A ball rolling down a hill is an example of potential energy converted to, kinetic energy. Okay, So ball rolling down a hill is an example of potential energy converting to kinetic energy. Now talking about maps, it says match the map's description to its name. So this map provides information about rainfall across an area of land. We would call that a thematic. Okay, so A goes right here, thematic. B, this provides features that are independent of elevation. This would be a planimetric. So B goes there. And then C provides elevation of an area of land, would be topographic. C right there. Number 6, why are two-dimensional maps not an accurate representation of the Earth? Well, the problem is the Earth is three-dimensional, and you will end up with distortion. Why are two-dimensional maps not an accurate representation of the Earth? The Earth is three-dimensional, and you end up with distortion. Number 7, energy flow. We're matching again, all right? So convection is what? Convection is where cool, dense air falls through warmer, less dense air, which is rising. Okay, so A goes right here. B, conduction is where we would see a hot marshmallow melting the chocolate of a s'more, because the chocolate is actually touching the hot marshmallow. That is called conduction. B right there. And then radiation is your face feeling warm from the sun. Walk out on a nice sunny day like today is, and you feel that heat, that is radiation. So C right there. Moving to Unit 3, what weather system, either El Nino or La Nina, might be occurring if Australia is experiencing droughts and parts of South America are flooded? That would be El Nino. Whereas if you have unusually warm ocean temperatures that are recorded in the equatorial Pacific, in other words, the Pacific Ocean at the equator, it'd be La Nina. La Nina. Okay? Now, define. An aquifer is an underground storage of water. Aquifer is an underground storage of water. Permeability, as it pertains to soil, is how well water flows through the ground. Permeability, when it comes to soil, is how well water flows through the ground. And then saturation is how much water is in the soil. How does water move in a zone of saturation? It moves sideways. How does water move in a zone of saturation? It moves sideways. Describe why ice floats using the word density. And I would say, well, ice is less dense than water. Ice is less dense than water. Define as it pertains to water. Condensation is the process of turning water from a gas to a liquid, and evaporation is the process of turning liquid into a gas. One more time, condensation is the process of turning water from a gas to a liquid, and evaporation, the process of turning liquid into a gas. Number 13, why would a civilization choose to live near a river that regularly floods? Because flooding deposits fertile soil onto the land. Flooding deposits fertile soil onto the land. Number 14, capillary action moves water through the ground. What force acts against this movement? And we see here that it is gravity. So again, capillary action moves water through the ground. What force acts against this movement? Gravity. Number 15, looking at the nitrogen cycle, okay? Does nitrogen travel through both plants and animals? Quite simply, yes. Does nitrogen travel through both plants and animals? Yes. What organism digests nitrogen in the soil? Bacteria. What organism digests nitrogen in the soil? Bacteria. If animals and plants both need nitrogen, why can't we get it from the air we breathe? Answer: atmospheric nitrogen is not suitable for plants and animals. Atmospheric nitrogen is not usable to plants and animals. So what changes the nitrogen into usable nitrogen? And it is bacteria again. So what changes the atmospheric nitrogen into usable nitrogen? Bacteria. What is eutrophication? And eutrophication is the supplying of extra nitrogen into a system, which in turn causes an algal bloom. Okay, in other words, too much nitrogen. So eutrophication is extra nitrogen in a system which causes an algal bloom. Okay. Number 16 is matching between the process and the atmosphere. So respiration, what happens in respiration? Well, we see right here that it removes oxygen from the atmosphere. That's what we do when we breathe. We take in oxygen, let out carbon dioxide. Photosynthesis actually removes carbon dioxide from the atmosphere. They're opposite of us. Photosynthesis produces oxygen by taking carbon dioxide out of the atmosphere. And then C, burning fossil fuels. See it right here. C puts carbon dioxide into the atmosphere. Okay, so it puts carbon dioxide back into the atmosphere. Number 17, match the layer of the atmosphere with the action. So troposphere, okay, troposphere is where we live in, okay, and that is where the weather happens. The ionosphere, which is up in the thermosphere, the ionosphere is where the aurora borealis happens. Those are the northern lights. C, stratosphere, is the highest point anyone has ever skydived. So C is there. And in your thermosphere is the warmest layer of the atmosphere. Right here's your thermosphere. Okay. Moving to Unit 7. Number 18, why do geologists think Earth's core contains mostly iron? It's because when we look at comets, they contain more iron than the Earth's crust. And we know that the Earth is made up of the combination of comets and asteroids and all this stuff coming together, we think. And so we know there should be a lot of iron, and that's the most dense material that naturally occurs here on Earth. So we think that's in the center, okay, because it's more dense, it fell to the bottom. Number 19, plate movement. So as we define these movements in plates, we come to a convergent boundary where you have two or more plates that come and collide together. Okay. Your divergent boundary, two or more plates move apart from each other. And then a transform boundary where two plates slide past each other. Okay. Now, looking at this, fill in the blank with a boundary that is the type of plate movement. An ocean ridge forms an example of this boundary, a divergent boundary, ocean ridge. Two ocean plates pull apart at this example of boundary. Again, it is a divergent boundary. New crust is created, an example of this type of boundary. Well, new crust is created at a divergent boundary again. And then a subduction zone forms as an example of this boundary, and it is convergent. Convergent. Now, Earth's magnetic poles. Approximately how often do the poles reverse? Every 200 to 300,000 years. So we say 250,000 years, approximately. And how do we know the poles reverse? Think about the oceans. And we see banding of the ocean floor. You'll see the floor down here somewhere. Of the ocean crust that shows different direction of alignment. Okay? So let me move that down a little bit so it's all together fair for us. All right, so here we go again. How do we know the poles reversed? And we see banding of ocean crust that shows different direction of alignment. In other words, bands of magnetic material in the crust, and it's aligned in different directions depending on when it was formed. When does the magnetic orientation lock into the rocks? As magma pushes through the crust, it solidifies. So as it comes up from the mantle, it's cooled and solidifies, and the orientation of those magnetic strips is set. Looking at waves, and especially seismic waves. So define, what is a seismic wave? A seismic wave is an energy wave that is created by the sudden movement of the planet's surface. An energy wave that is created by the sudden movement of the planet's surface. What is reflection? Reflection is when waves bounce back when coming into contact with a change in phase. In other words, you're going from liquid to solid or solid to liquid. Okay, we get reflection, that is the bounce back. And then refraction, waves change direction as they cross the boundary of a change in phase. An example, going from solid to a liquid or a liquid to a solid. Now, this one says when a P wave crosses from solid to liquid, it will bend in the process of refraction. Refraction. And then C, when a P wave bounces back from a barrier, it will bend in the process of reflection because it's bouncing back, reflection. Number 8, or 22 in Unit 8, number 22, earthquakes, okay? Now, how much more energy does a 6.0 magnitude earthquake have than a 4.0 magnitude earthquake? Well, magnitude increases by a value of 10 each time you go up once in one increment on the scale. So since there's an addition of 2, it would go up by 100 times. So from 4 to 5, you get 10 times the power. And then from 5 to 6, you get another 10, which is actually 100 times from 4. So it would increase 100 times. Number 23, define these types of weathering. Okay, so weathering that requires water. Well, water can cause mechanical and chemical weathering. So both mechanical and chemical weathering can have water. Hydrolysis, okay, is chemical weathering where minerals break down in water. Hydrolysis is chemical weathering where minerals break down in water. Frost wedging is where mechanical weathering caused by the expansion of water as it freezes and is confined in a structure. Ooh, what just happened there? All right. So frost wedging is mechanical weathering caused by the expansion of water as it freezes and is confined in a structure. A solution. Okay. Looking at weathering that does not require water. Okay. Not all mechanical weathering needs water. Wind, traffic, and gravity are all sources of some types of mechanical weathering. So again, not all mechanical weathering needs water. Wind, traffic, and gravity are all sources of mechanical weathering. What is oxidation? Oxidation is weathering caused by the combination of oxygen and other substances, usually iron, in rocks, which causes the rocks to weaken and crumble. So again, oxidation is the weathering caused by the combination of oxygen and another substance, usually iron, in rocks, which causes the rocks to weaken and crumble. Number 24, erosion. Define erosion. Erosion is the carrying away of weathered material. The carrying away of weathered material. How is erosion different from weathering? Weathering is the breaking down of material like rocks. Erosion is the carrying away of material after it has weathered. Okay, so how is erosion different from weathering? Weathering is the breaking down of material like rocks, and erosion is the carrying away of that material after it is weathered. And C, which of these three could cause erosion. Actually, they all could. But specifically, gravity, water, and wind can cause erosion. But animals can too. They can carry dust with them as they move along, or other living things. Um, I guess trees could. Well, they do a lot of weathering. So, but specifically, focus on gravity, water, and wind. Now, what causes tsunamis? Let me move this down here so it's together as well. All right. Tsunamis are underwater seismic activity, usually earthquakes or volcanic eruptions that cause huge amounts of energy to transfer through a large body of water. Okay. Again, what causes tsunamis? Underground seismic activity, usually earthquakes or volcanic eruptions that cause huge amounts of energy to transfer through a large body of water. Number 26. Why do earthquakes often happen near subduction zones? Subduction zones have low granite content. This movement of the crust as it goes over or under causes friction, releases energy in the form of an earthquake. B, subduction zones have weak rocks. They are under tremendous pressure, and as the crust is subducted back into the mantle, it begins to melt, weakening it. C, subduction zones are near volcanoes. The increase of volatility around the melting crust causes a buildup of magma, and it escapes through the crust above it. And subduction zones are near plate boundaries, usually continental versus oceanic crusts, where the oceanic will subduct below the continental. Number 27. Other earthquake terms to define. What is a focus? A focus is placed down in the crust where the earthquake originates. So focus is placed down in the crust where the earthquake originates. The epicenter is a place on surface that is right above the focus. So that would be like a place on a map. Okay. Then a fault is any break in the surface of the crust caused by seismic activity. Fault is any break in the surface of the crust caused by seismic activity. And then intensity. It is the perceived amount of energy caused by an earthquake, often measured in damage. Okay? The perceived amount of energy caused by an earthquake, often measured in damage. And Unit 10, half-life calculations. Okay? A radioactive element has a half-life of 1,000 years. If a sample of this element begins with a mass of 100 grams, how long would you have to wait for the mass to decrease to 25 grams? The answer: after 1,000 years, the sample would be down to 50 grams, which is half of 100. Then it would take another 1,000 years for that to decrease to 25 grams, which is half of 50. So in total, it would take 2,000 years for the element to decay to 25 grams. You see here, we start at 100 grams, we go 1,000 years, and we're at 50 grams. And in another 1,000 years, we're at 25 grams. So a total of 2,000 years. B, a radioactive element has a half-life of 4,000 years. If a sample of this element begins with a mass of 100 grams, how long would you have to wait for the mass to decrease to 25 grams? So this is just like above. We see that 100 grams has to go through two halves to get to 25 grams. And each half-life is 4,000 years. So it would take 8,000 years to go from 100 grams to 25 grams. Okay, so again, 100 grams, you start at 100 grams, you go 4,000 years, you're down to 50 grams. And you got to go another 4,000 years, and you're down to 25 grams. And here's a video to watch. You can copy and paste and put this into your bar at the top, and it'll kind of go over it for you as well. Number 29, atmospheric changes. Okay. Volcanoes change Earth in the first 2 billion years by outgassing what? Well, there's all kinds of gases. We had hydrogen, we had carbon dioxide, nitrogen, and other gases that were relative to those, but no oxygen. So what gas that we depend on today did not come from and produced in the Precambrian area? Oxygen. Okay, oxygen was not produced by these volcanoes. So, C, how did Earth's atmosphere become oxygen rich? There were single cell organisms like bacteria producing oxygen through photosynthesis. So bacteria like organisms producing oxygen through photosynthesis. Number 30, mass extinction happened at the end of which two eras? The Mesozoic and the Paleozoic. Again, number 30, mass extinctions happened at the end of which two eras? The Mesozoic and the Paleozoic. Number 31, what happened at the end of the Mesozoic era but did not happen at the end of the Paleozoic era? And we had a major asteroid impact. Both ended in mass extinctions, but the Mesozoic ended in an asteroid impact. The Paleozoic was more volcanic. And 32, why are there no samples of rocks from the early Precambrian era? They were all molten. They were all still melted, right? So again, 32, why are there no samples of rocks from the Precambrian era? They were all molten. All right, guys, I sure hope that helps out. If you have any other questions, please let me know. And if not, I will talk to you soon. Good luck on this. And please keep in contact with me. Again, if I can help you with anything, please let me know.